Hello, curious minds. Imagine a star so dense that a single teaspoon of its matter would weigh more than Mount Everest. This is the reality of a pulsar, one of the most mysterious and fascinating objects in space. So, what exactly is a pulsar? Imagine a star, much more massive than our Sun, reaching the end of its life. The star collapses in on itself, squeezing its core tighter and tighter. This process, my friends, is a supernova explosion. The outer layers of the star are blasted out into space, but the core, the core is something else. It becomes incredibly dense, cramming more mass than our Sun into a sphere just a few miles across. And here's the kicker: this dense core, now called a neutron star, is spinning incredibly fast. They have these incredibly strong magnetic fields, trillions of times stronger than Earth's. These magnetic fields channel charged particles from the poles, creating beams of radiation that sweep across space like a lighthouse beam cutting through the fog. As these beams sweep past Earth, we detect them as pulses of radiation, hence the name pulsar. When pulsars were first discovered back in 1967, it was radio waves that gave them away. Jocelyn Bell Burnell, a graduate student at the time, noticed these regular pulses of radio emission coming from a specific point in the sky. At first, they thought it might be aliens. Seriously. They even jokingly called the first pulsar LGM-1, which stood for Little Green Men. But as more pulsars were discovered, it became clear that these weren't signals from extraterrestrial civilizations but something even more fascinating. These radio pulsars, as we call them, emit radio waves, a type of electromagnetic radiation, from their magnetic poles. These radio waves travel through space, and if Earth happens to be in the path of the beam, our radio telescopes pick them up as those characteristic pulses. Their precise pulses act like cosmic clocks, allowing us to study all sorts of phenomena, from the properties of interstellar space to the nature of gravity itself. Now, if you thought regular pulsars were fast, hold on to your hats, because millisecond pulsars take the concept of rapid rotation to a whole new level. These extraordinary objects are not just fast, they are mind-bogglingly fast. These speed demons spin hundreds of times per second, making them some of the fastest spinning objects in the known universe. Their speed is so incredible that it challenges our understanding of physics. To put that into perspective, imagine our Sun, which takes about a month to rotate once. Yes, a whole month for just one rotation. Now picture the Sun spinning hundreds of times in a single second. It's almost beyond comprehension. But how do these millisecond pulsars get up to such incredible speeds? What cosmic forces are at play here? Well, it's all thanks to a little cosmic cannibalism. This process is as fascinating as it is dramatic. You see, many millisecond pulsars are found in binary systems, where they have a companion star orbiting them closely. This close relationship sets the stage for an extraordinary interaction. As the companion star ages and expands, it begins to lose material. It spills material onto the pulsar, transferring mass in a spectacular cosmic dance. This transfer of mass spins up the pulsar, increasing its rotational speed dramatically, much like a figure skater pulling their arms in during a spin. The physics are similar, but the scale is cosmic. Their precise timing makes them incredibly valuable tools for studying a wide range of astrophysical phenomena. Scientists rely on these pulsars for their remarkable accuracy. So far we've talked about pulsars that emit radio waves, but the electromagnetic spectrum is vast, my friends. It spans from the longest radio waves to the shortest gamma rays, each with its own unique properties and mysteries. Enter X-ray pulsars. These cosmic powerhouses emit X-rays, a form of electromagnetic radiation with much higher energy than radio waves. X-rays are incredibly energetic and can penetrate through materials that would block other types of radiation. Now, unlike radio pulsars where the emission comes from the magnetic poles, X-ray emission from pulsars usually originates from the pulsar's accretion disk. This disk is a crucial component in the life of an X-ray pulsar. As material from the companion star falls onto the pulsar, it forms a swirling disk of superheated gas, kind of like a cosmic whirlpool. This process is both fascinating and violent as the material heats up to millions of degrees. This accretion disk gets so hot that it emits X-rays, and because the pulsar is spinning, we see these X-rays as pulses. The rapid rotation of the pulsar creates a lighthouse effect, where the X-rays sweep across space. Some X-ray pulsars, known as accreting X-ray pulsars, are actually neutron stars in binary systems where the companion star is a massive star. These systems are dynamic and complex, with the neutron star's gravity playing a pivotal role. The intense gravity of the neutron star pulls material off its companion, forming that accretion disk and producing those powerful X-ray emissions. This interaction between the stars is a dramatic dance of forces. Detecting X-ray pulsars requires space-based telescopes, as X-rays cannot penetrate Earth's atmosphere. Studying these X-ray pulsars allows us to probe the extreme environments around neutron stars and learn more about the physics of matter under extreme conditions. Now we're about to enter the realm of gamma-ray pulsars, the true heavyweights of the pulsar family. These pulsars crank the energy output up to 11, emitting the most energetic form of light in the electromagnetic spectrum, gamma rays. We're talking about photons with energies millions of times higher than visible light. Now, gamma-ray pulsars are relatively rare, but they're incredibly important for understanding the most extreme processes in the universe. These pulsars are like the cosmic particle accelerators, generating intense beams of gamma rays that blast through space at nearly the speed of light. One theory is that the gamma rays are produced in the pulsar's magnetosphere, the region of space dominated by the pulsar's magnetic field. As charged particles are accelerated in this intense magnetic field, they emit gamma rays. Detecting gamma-ray pulsars requires space-based gamma-ray telescopes, since Earth's atmosphere blocks gamma rays from reaching the surface. In the vast expanse of space, even the most extreme objects sometimes form a close relationship with a partner. And when that partner is another neutron star or a black hole, well, things get really interesting. We're talking about binary pulsars, systems where two pulsars orbit each other in a celestial waltz. Now, binary pulsars are more than just a cosmic curiosity. They're incredibly valuable tools for studying gravity, one of the fundamental forces in the universe. According to Einstein's theory of general relativity, massive objects like neutron stars should warp the fabric of spacetime around them. And when these objects orbit each other, they create ripples in spacetime, kind of like the waves you make when you drop a pebble in a pond. Binary pulsars provide us with the perfect natural laboratory to test Einstein's theory and study these elusive gravitational waves. By precisely measuring the timing of the pulses from these systems, astronomers can detect tiny variations caused by the gravitational pull of the companion object, allowing them to study the effects of gravity in extreme conditions. A famous example is the Hulse-Taylor binary pulsar, which provided the first indirect evidence of gravitational waves and won the Nobel Prize in physics. Now, just when you thought the world of pulsars couldn't get any stranger, we have RRATs and Magnetars, the weird and wonderful cousins of the pulsar family. First up, we have RRATs, which stands for rotating radio transients. These mysterious objects were discovered quite by accident, and they are like the shy members of the pulsar family, only flashing us with brief bursts of radio emission every now and then. Unlike their more predictable pulsar cousins, RRATs are sporadic and unpredictable. Imagine a lighthouse that only flashes its light for a fraction of a second every few minutes or even hours. This makes them incredibly challenging to study. We're still trying to figure out what makes RRATs tick, and why they behave so differently from regular pulsars. One theory is that they're just regular pulsars with beams that are either very narrow or not pointed directly at us most of the time. This could explain their elusive nature. Now, on the other end of the spectrum, we have magnetars, the true behemoths of the magnetic field world. These neutron stars are not just powerful, they are extreme in every sense. These neutron stars have magnetic fields that are absolutely mind-boggling, trillions of times stronger than those of regular pulsars. To put it in perspective, if a magnetar were located halfway to the moon, it could wipe the data from every credit card on Earth. Magnetars are also known for their powerful bursts of X-rays and gamma rays, which can release more energy in a fraction of a second than our sun emits in hundreds of thousands of years. These bursts are so intense that they can affect the Earth's atmosphere, even from thousands of light years away. These bursts are thought to be linked to starquakes or sudden changes in the magnetar's magnetic field, making them some of the most dramatic events in the universe. So far we've explored the different types of pulsars and their incredible properties, but what about the science behind these cosmic lighthouses? What makes them tick? Well, at the heart of it all is a fascinating interplay of gravity, electromagnetism, and nuclear physics. Let's start with gravity. As we discussed earlier, pulsars are born from the death of massive stars, which collapse under their own gravity to form incredibly dense neutron stars. These neutron stars pack more mass than our sun into a sphere just a few kilometers across. The intense gravity of these objects is what drives their rapid rotation and generates their powerful magnetic fields. Next up, we have electromagnetism. As these neutron stars rotate, their magnetic fields interact with the plasma surrounding them, creating powerful beams of radiation. Pulsars are essentially giant spinning magnets, with magnetic fields trillions of times stronger than Earth's. The exact mechanism by which these beams are produced is still a subject of active research, but it involves complex interactions between the pulsar's magnetosphere, where charged particles are accelerated to near-light speeds, producing the radiation we detect as pulses. And finally, we can't forget the role of nuclear physics. Neutron stars are so dense that their matter is in a state unlike anything found on Earth. Inside a neutron star, protons and electrons are crushed together to form neutrons, creating a core of almost pure neutron matter. The extreme conditions inside these stars, such as the balance between gravity pulling matter inward and neutron degeneracy pressure pushing outward, are crucial to understanding why pulsars remain stable over incredibly long periods. As we've journeyed through this cosmic exploration, we've encountered some of the most extreme and fascinating objects in the universe. We've learned that pulsars are more than just spinning neutron stars. They're cosmic laboratories that allow us to study the fundamental laws of physics, from gravity to electromagnetism to nuclear physics. They're timekeepers, providing us with the most precise clocks in the universe. And they're storytellers, revealing the secrets of stellar evolution and the extreme conditions that exist in the aftermath of a supernova explosion. As we continue to explore the universe, pulsars will undoubtedly play an increasingly important role. Their unique properties make them ideal tools for studying a wide range of astrophysical phenomena, from the search for gravitational waves to the mapping of the interstellar medium. With new technologies and missions on the horizon, our understanding of these cosmic lighthouses is poised to deepen, offering new insights into the mysteries of the universe. Pulsars are amazing reminders of how much there is left to discover in our universe. From their rapid spins to their powerful emissions, these stars continue to surprise and inspire us. What do you find most fascinating about pulsars? Do you think they might help us unlock more cosmic mysteries? Let me know in the comments. If you enjoyed this video, don't forget to like, subscribe, and hit the notification bell for more exciting space content. Until next time, keep looking up.